Welcome to part two of looking at some of the sorting algorithms that the book has specified. So where we left off last time, we were looking at the timing that it takes to do a merge sort versus a selection sort, depending upon the number of items in an array. As you can see, both graphically and in the table, the merge sort is a lot faster than the selection sort. So what we're going to do next is we're actually going to run both the merge sort and the selection sort in JGrasp using the stopwatch class that the book has created. So what I need to do first is I need to go into my selection sort timed class, and basically what I've done in there on line 17, I've created an instance of the stopwatch. I've started the timer on line 18. I've called my sort method, and then on line 20 I'm stopping the timer, and then on line 21 I'm displaying the time it took to complete the sort algorithm. So this is for the selection sort. Again, when you want to go ahead and time an algorithm, you want to make sure you start the timer right before you call the method that the algorithm is coded under, and then you stop the time after that method has completed. So let me just go ahead and click on the Run button. So again, the array has 100,000 items, and it can have a random number between 0 and 999,999. So it looks like the selection sort ran in about 3.129 seconds. So what we're going to do next is we're going to go ahead and run the merge sort. So we will go ahead, kick it off. It has the same where, again, it's an array of 100,000 items, anywhere between 0 and 999,999. So I will go ahead and kick it off. Again, I've created an instance of timer and started and stopped the timer before the sort method was called, and stopped it after the sort method completes. And this completed quite a bit faster. It took us 0.044 seconds to go ahead and sort an array that had 100,000 items. So you can definitely see that the merge sort is a lot faster than the selection sort. And what we're going to do next is we're going to look at one final sort, and what that is the quick sort. So let me just go back into the presentation. So the quick sort algorithm, there's no temporary arrays are created. It's a divide and conquer. You partition the range and then you sort each partition. In the quick sort, one partitions the elements into two groups, holding the smaller and larger elements, then sorts each group. So again, what I've done is I've created a class that you can go ahead and run in. So I think I've actually copy and pasted that quick sort into the visualizer tool, so it's out there. Quick sort has 4 items. Again, we need to limit it so we can actually see the visualization execution, so we don't create an error message. So again, we're in the method. We go ahead, we create the array, we called sort A. Basically what sort A does is it passes the array, and then it calls another sort method, passing in the array 0 and the length of the array -1. So we'll click on the next, and then what it does now is it goes in, it goes as long as from is greater than or equal to 2, as long as 0 is greater than or equal to 3. If from is greater than or equal to 2, we'll return. Otherwise, we go ahead and call our partition function, passing it in from and to an A, and then now it walks through the partition function. So feel free to go ahead and walk through the rest of the quick sort using the visualizer tool, so you can kind of see how the code and how the algorithm works. So on average, the quicksort algorithm is in big O notation of n log n, and its worst case runtime behavior is n squared. So if the pivot element is chosen as the first element of the region, that worst case behavior occurs when the input set is already sorted. So that's all I wanted to cover in part 2 of the video. So what we're going to be covering next is we're going to be looking at a couple of search algorithms. So we will talk to you next time.